All right. Hey, everybody. We're continuing this lecture series, maybe finishing up by today. Where we are now is prediction of metabolism, sites of metabolism, and also the metabolite structures, specific metabolites that might be produced by phase 1 and 2 metabolism. So last lecture we had a problem with one of the servers. It's called the nerd server, which is it does several things related to metabolism. I actually contacted the people that run the server, and they got it working again. It's actually this lab by Professor Johannes Kirschmeer. He's at the University of Hamburg. I think he's maybe moving to University of Vienna in Austria, and so it's a pretty cool international developed tool for metabolism. And I think what his research is with his group members is kind of looking at chemical structure and predicting metabolism. So looking for different functional groups or maybe parts of a molecule that might be susceptible to metabolism. So they actually create these kind of computational tools that allow us to predict metabolism. So it's not totally obvious how to do that, and I think a lot of it is using experiment and kind of known fragments of structures and just known metabolic routes, and being able to predict them computationally. Anyway, so that just showing that's actually an area of research that people do, and also shows that it's an area of research that is kind of computer-based and not necessarily something where you work in the lab. And there's a lot of research like that, thinking about like coronavirus and sort of career paths. A nice thing about computational research is you can do it remotely. Like I do some computer research myself, and I'm doing those experiments currently from my house, connecting to remote servers. Anyway, that is a little bit on this nerd server and the lab that maintains it. Okay, so yeah, we will talk about the nerd server, which is called New E-Resources of Drug Discovery, which is University of Hamburg. I think also maybe University of Vienna, Austria, University of Technology in Prague, Czech Republic, and University in Milano, Italy. We already talked about the Biotransformer server, which I'm not going to talk about again, but it was a structure predictor for phase 2 metabolism. So it kind of would look at a molecule and figure out where the phase 2 conjugation might occur. Remember that phase 1 metabolism is kind of the introduction of functional groups that aid in the excretion of a molecule. Phase 2 is beyond that. It's actually attaching other molecules. Okay, so prediction of metabolism. Let's first do the nerd server. And this is the URL. So I checked it. It is working today. I think what happened was they had a power outage at the University of Hamburg, and it killed the power supply and did some sort of computer hardware problems. And anyway, that's all fixed now, so this works. And the things we're going to demonstrate on this nerd server, they all provide complementary information, are something called chem477, which just identifies the sites of phase 1 metabolism, so places on the molecule where phase 1 metabolism might occur. And also they have a tool for the sites of phase 2 metabolism, just identifying where on the molecule phase 2 metabolism might occur. And then they have another tool called Glory, which predicts the structure of metabolites, and that's sometimes kind of difficult to figure out, what structures might occur. In the real world, when we're investigating drug metabolism, we often have no idea, and it's not totally obvious what the structures are. And if we synthesize a molecule and we do metabolism study, and then we analyze the products of the study, we don't necessarily have any idea what the structures are. So it's a really difficult challenge. Usually you don't have enough material for NMR, because NMR will tell you the chemical structure pretty easily. But we usually have mass spec, and so we know the molecular weight, and we can sort of make predictions based on the molecular weight differences of the drug and the metabolite. All right, so let's jump onto the nerd server. We're going to first do the FAME3 utility, which predicts the sites of phase 1 metabolism on the molecule. Okay, and before we do that, let's think about what sort of phase 1 metabolism might occur for this molecule. This is a tricyclic antidepressant, disipramine. Thinking about phase 1 metabolism, what would you predict might happen, and what the sites might be? Like where are the likely conjugation, not conjugations, because phase 1 isn't conjugation. Phase 1 is introduction of functional groups, and so typically, I mean, when I look at a molecule like this, I would look for sites maybe next to a heteroatom, like maybe next to a nitrogen. A heteroatom is something with a lone pair, electronegative groups that might stabilize a radical. So like this position could be a stabilized radical by the nitrogen. This position could be a stabilized radical because of this nitrogen. This position is also kind of a stabilized radical due to the nitrogen. And also, where else in the molecule? And these are next to a heteroatom. What other positions are maybe stabilized by a neighboring group? Well, certainly the alkyl CHs up here, which are next to a benzene. Because if you imagined a radical right there, the radical could be localized onto the benzene. Same with this side. So I'm kind of, my predictions might be, well, this could be a site of metabolism, this could be a site of metabolism, this could be a site of metabolism. Maybe that could be a site of metabolism. What else can happen with phase 1 metabolism? Well, benzenes can be hydroxylated. And so you can maybe imagine a hydroxy group maybe on a benzene. Those are all predictions. I don't know. We'll see what this server says. Okay, so here's the SMILES string, and we can input the SMILES string onto the server. So I'm gonna go get that SMILES string. Okay, so I put it on the server, or on the clipboard. Okay, here's the nerd server. Let's refresh it and make sure it's still working. So I went to this nerd.zbh uni Hamburg, and DE is Germany, and I'm going to refresh the website. Okay, so we're connected to the server, and what we're going to do is the FAME3 sites of metabolism tool, which is this left button. All right, and we're going to there's prediction of phase 1 and phase 2 sites of metabolism. We're just going to do phase 1 for now. We're just going to click the phase 1 metabolism site button, and I'm going to paste that SMILES string. Let's delete the spaces before it. Okay, and let's try it out. So I'm going to click the submit. Okay, so it's running now. Your results will be available at this site. So it gives a link to where the results will be, but it'll just take a minute. So hang out a second. Oops. Okay, so the prediction is complete. It did its analysis. It says predictions are successful for 1 out of 1 input molecules. Download the results here, or I can just go down and say, let's go to the results, and we don't have to download anything. Just click it. Okay, so what it's doing, what it's showing here, maybe I'll maximize the window, is it shows where they call them hotspots, the hotspots of where metabolism might occur, and it's giving a probability. That's I'm not sure what the difference of probability and fame score is, but they're both relative measures of the likelihood of metabolism at these different positions. And so and it gives numbers, right? C1, N2, C5, C3, and how do you know what those numbers are? Well, in this tool you can move the mouse over the molecule, and then we see, okay, C1, the probability is 0.804. So is that a high probability or a low probability? Well, that's a pretty high probability. That's like 80% probability that C1 is going to be metabolized, right? And that's kind of as expected. That's one of the ones that we predicted. Why would C1 be metabolized? And that is because it can be demethylate. And demethylation, oxidative dealkylation, was one of the key metabolism reactions we talked about, right? So what happened is C1 here would get hydroxylated, and then the oxygen would kick off the nitrogen, and then the net effect is loss of the methyl. That's oxidative dealkylation. So that is actually, and it gives a pretty high probability that's going to happen. N2, so N2 is this nitrogen. We did not predict that a second ago, but yeah, that's actually likely too, because remember the other one of the reactions is direct oxidation of nitrogen, and I think we may have actually shown this back in the metabolism slides. I have to look at it, but that's a pretty high probability metabolite. Also, is an N oxidation. What other positions? So these are the hotspots, like the most likely things. There are other possible metabolic sites that are maybe a little less probable. So C5 and C3, where are those? Okay, just like we said, actually, C5 and C3. So those are next to this nitrogen and next to this nitrogen. Well, those are possible, but maybe a little less probable. Okay, C17, it's saying C17 is maybe the next one. Okay, well, yeah, that's actually aromatic hydroxylation, we'd imagine. So hydroxylation of the C17 position. Those are all things we've seen in our metabolism slides previously. It's also showing, with lower probability, C13 and 14, so next to the benzene ring. And then kind of everything else is just really, really low probability. Okay? So most of the things that we actually mentioned were shown, with a couple being higher probability. Okay? All right, so let's, we'll go back. Okay, and so that was disipramine, and basically what it was showing was things related to this terminal nitrogen. Either oxidative dealkylation of the methyl is probably what is going to happen. High probability that the CH3 would be metabolized, and probably to alcohol, and then later it would kick it off. And the other thing is maybe direct metabolism of the nitrogen. Okay, how about this molecule? This is alprazolam. Alprazolam is also called Xanax. It's a benzodiazepine sedative type drug. All right, and so what sort of predictions might you have of this molecule that might be metabolized? I mean, looking at the molecule, I kind of think, I don't know, what do you think? It's hard for me to have you answer when I'm just recording stuff, but yeah, I could imagine, you know, maybe the CH3 might be metabolized. Why would I say the CH3? Well, it's next to a pi bond, and so it could stabilize a potential radical at the CH3 position. This position kind of stands out to me because it's next to a nitrogen and it's also next to the this double bond over here. And I also see the aromatic ring, and I kind of think this position here maybe looks like a possible metabolic site. We did learn that a para-hydroxy group, so like a hydroxy group on an aromatic ring that is para to some other part of the molecule, might be hydroxylated. So I'm kind of, you know, naively guessing that one. I think maybe a little less likely on this benzene because of the chlorine kind of blocking things. And let's see what happens. Okay, so there's a smile string. Let's get it. So I'm gonna copy it to the clipboard. It's on the clipboard. All right, and let's go back to the nerd server, and we're still in the phase 1 metabolism section of FAME3. Let's paste that molecule in. I'm going to delete the leading spaces. Okay, so we got the smile string inside. This also does cool things where you can upload a list of smile strings. So if you have like 100 molecules, you could analyze them all simultaneously. SDF, again, we've mentioned, is another file format for molecules. This is closer to PDB, I guess you'd say. It has the three-dimensional structures usually inside. Anyway, for now, though, we're just doing individual smile strings. It's nice because we can copy and paste them. This server also allows you to draw a molecule if you want to just draw it yourself. All right, so let's submit Xanax into the server. And there it goes. And what are my predictions again? We'll see if my predictions are reasonable, but I kind of thought the CH3, maybe the CH2, maybe the aromatic ring. If I had to do 3 possibilities, maybe the nitrogens, but these kind of nitrogens aren't like a normal amine like these amines were, and so I would maybe feel less likely about them, but I don't really know. Yeah. Okay, it's done. Let's take a look. So we can download the results or just click down here and okay, so well, the circled things are the hotspots, and yeah, that prediction was actually pretty right from my perspective, that C16 and C1 are hotspots with kind of high probability of oxidation. And remember, to see the numbers, you move your mouse over the structure. I think you can do this on a tablet also, but there's probably a way to like click it so you can see the numbers. Otherwise, probably do this on a computer. Okay, what else? And so C20, yeah, it's lower probability, but like I was kind of saying, you know, parahydroxylation of a benzene is a pretty reasonable metabolic fate of a molecule. We saw that in Atenolol. We saw some examples of this when we're talking about metabolism. Everything else is pretty low probability. So pretty much the 3 things are the oxidative metabolism of position 1, oxidative metabolism of position 16. How do we know it's oxidative? Well, it can't be reductive, and it can't be hydrolytic. So it's most likely going to be like hydroxylation of 1, hydroxylation of 16. If I was making a guess on position 20, I would say hydroxylation of the benzene at position 20. Cool. All right, so those are deciperamine alprazolam, Xanax. Let's try the nerd server for phase 2 metabolism now. And that's, we kind of showed this with that other Canadian website last time. And let's try it also with the nerd server. And this is just going to show the probability of phase 2 metabolism. So let's try disipramine again. So this tricyclic antidepressant. And in terms of, again, what FAME3 is going to do is determine the probability of metabolism. And so not necessarily what the metabolites are, but what the probability is. And are there any predictions on which of these atoms might accommodate a conjugate, like in phase 2 metabolism? Something maybe that's nucleophilic. Well, as you probably remember, hopefully, yeah, simple atoms that are nucleophilic might be good phase 2 metabolism sites. And the one that sticks out is clearly the secondary amine. So this nitrogen could get glucuronidated or maybe sulfated, but I don't think amines are amine sulfate bonds are very stable. So I think that's usually an oxygen thing. But glucuronidation of this nitrogen could happen. You could maybe get acetylation or other things like that. Okay, so those are my predictions. I would say high probability of nitrogen being a phase 2 metabolism site. Okay, and I'll copy that onto my clipboard. Okay, this is on the clipboard. Now we're back into the nerd FAME3 tool. Let's go back. And okay, so now we're going to click phase 2 metabolism. Is it going to work? My mouse is weird with this yellow background. Okay, delete, paste. Okay, so now we've pasted disipramine back into the input string. Okay, and submit. And run phase 2, right? Yeah, phase 2. Click, submit, go. All right, prediction successful. Let's show the results. And with perfect, pretty extreme probability, it's saying exactly what we predicted, that the secondary amine would be the site of phase 2 metabolism. Okay? Yeah, I mean, this would be possible. I would say C6 is possible, but since it's tertiary, it's kind of hard to attach stuff to it without becoming a quaternary ammonium. I'm a little surprised it's 0 probability, but it C or N6. But not too surprised. I think N2 is very that makes sense. Okay, good. So let's go back and we'll try the next molecule. Okay, so that kind of agreed with our predictions. Okay, Atenolol, which is a beta blocker, beta adrenergic receptor antagonist. It's got an alcohol, a secondary alcohol. It's got a tertiary amine, and it's got this primary amide. Okay, so if we're thinking about phase 2 metabolism, what sites of this molecule might you predict would be likely to be metabolized? Again, for phase 2 metabolism, you're mostly looking for nucleophilic atoms. And I'm kind of thinking, well, that secondary alcohol is kind of poking out like a sore thumb. Alcohols love to be phase 2 metabolized. The secondary amine seems possible. It's a little sterically hindered because of the isopropyl group, right? Isopropyls kind of might get in the way of phase 2 metabolism, but still, you know, I'd say alcohol high probability, nitrogen possible but maybe lower probability. This amide is possible, although amides are kind of stable functional groups and resonance stabilized type of functional groups. So yeah, possible, not likely. Nothing else really stands out. Carbon, no. You know, the ether is a nice happy functional group. There's no nucleophilic character. So I'm gonna if I was placing a bet, I would say probably the oxygen, maybe that nitrogen, and possibly this one, but maybe a extremely low probability. Let's see. So there's the smile string, and let's go get it. Copy. Okay, so I put this Atenolol smile string onto the clipboard. Let's give it a shot. And here is the phase 2 nerd server with the FAME3 utility. Paste the smiles. I'll see if it does it with the leading spaces. Submit. There it goes. I should say I think when you get older, you start taking these a lot of these kind of beta blocker drugs for hypertension, and I don't know. What I found is getting a little older, I've had maybe a slightly higher blood pressure, and I've actually taken drugs like these beta blockers. They work really well at kind of having an anti-hypertensive effect, but for me, it causes incredible insomnia. I actually stay up all night long if I take drugs like this, and so I had to stop taking it just so I can get sleep. So anyway, there's something interesting about beta blockers, and I don't know. I've got to talk to my doctor about that. So, but that is a common side effect of beta blockers. Really good at beta adrenergic antagonism, but have some weird side effects. Oh yeah, nightmares. People have nightmares. I didn't have nightmares. Okay. Results. Let's take a look. And well, it puts calling oxygen 19 a hotspot, and that totally makes sense that a secondary alcohol would be a hotspot. Yep. And so it's higher probability for that, and then N18. What's that one? So it's actually ranking the primary amide maybe higher than N4, and you know that actually kind of makes sense, because what I was predicting just a second ago was that this would be high probability, this would be medium probability, this may be lower probability. But the reason I was suspicious of nitrogen 4 is because of steric hindrance. I think the isopropyl could maybe get in the way. But N18 doesn't have that. It has a primary amide that clearly just kind of pokes out off the molecule, and so that could actually be maybe a better hotspot. or site of metabolism. Neither of them are really hot spots with a high probability. But you could imagine metabolism of the amide and the secondary amine, and this server is predicting the amide to be maybe a little more reactive. Yeah, that's reasonable. Okay, so that was FAME3 server showing the probability of metabolism of this molecule. Okay. All right. So let's look at the nerd server for and using this other tool, not the FAME tool, but it's called Glory, for metabolite structure prediction. And so this will maybe predict phase 1 metabolites in a molecule, the specific reactions that might occur. So we're going to go back to disipramine, the tricyclic antidepressant, and kind of now think about specific reactions that might occur. So not just the probability, but the actual reactions that might occur in this molecule. What do you think those reactions might be? Okay, going back to our knowledge of phase 1 metabolism, and we're going to use Glory for phase 1 metabolism. I think what we found, at least currently, was that the Canadian website that we were looking at was maybe a little better for the specific conjugation and looking for glucuronidation and phase 2 metabolism. But let's think about phase 1 metabolism. What might happen? Maybe thinking about this area, which was the hot spot. What type of reaction might occur here? And I would say, like we were saying before, that this could be maybe hydroxylated and then oxidatively dealkylated. So hydroxylation, then oxygen kicks it off and makes the primary amine, NH2, right? That's one thing that I could imagine. Another thing I could imagine is hydroxylation of this position, and maybe it kicks it off to make an aldehyde, or maybe a carboxylic acid. Those are my predictions. Anything else? Maybe hydroxylation, or maybe hydroxylation of one of the CH2 sites, right? So let's see what the Glory server predicts for metabolite structures of this molecule. So there's our SMILE string. Let's get it. Copy. Whoops. Copy. Okay, and let's go back. We're going to go back even further. So now we're going into the metabolite structure tool, which is called Glory. This seems like a pretty cool thing. We may have to take a look at this in one of our future lectures. I think what this is looking for is something called promiscuous inhibitors, which are inhibitors that are found. They might be they might seem always active when you do assays, but they're not really active. It's kind of hard to explain. I'll have to get back to this promiscuous inhibition. But this is a tool that predicts that. And it has a little bloody hand, which would suggest it's like a villain or something. So certain molecules, though, we kind of try to avoid because as drug screening hits, because of their structures are associated with maybe fake activity, we'll say. Okay, let's go to Glory. All right, so Glory, and we're going to predict cytochrome P450 metabolites. Okay. Let's try it again. Okay, and we hold on to this max coverage default. Let's let it run. Our predictions are probably oxidative dealkylation of the methyl, maybe oxidative dealkylation of this side, maybe hydroxylation up here, maybe hydroxylation of a benzene. Those are my guesses, kind of based on what we saw before. Alright, so it came up and we can download, or we can just look at the results. We'll go to the results. Okay, so the way this is arranged, I'll maximize the window. Here's the input molecule. Let me see if I can, a little hard to see, but there's the input molecule, okay? And then we have, okay, so there we go. One of the, actually this is maybe a high ranking one in terms as a possible metabolite. This is hydroxylation of the benzene, and that's opposite to the nitrogen, because I think that position's maybe stabilized. Yeah, so that's one of the possible metabolite structures that this server is predicting. This one now we're showing hydroxylation of the methyl, which seems like a pretty reasonable thing that might happen. Remember, this is usually not stable, so this might happen, but then the oxygen kicks off to make formaldehyde, right? So oxygen kicks off, this breaks off, and then you get a primary amine, and then formaldehyde. But yeah, that's predicted, and I think this is showing N-hydroxylation of the nitrogen. Now, remember, these things can do further metabolism, and we talked about that also in the metabolism slides. So there's some maybe subsequent metabolism of after N-hydroxylation. And then what do we got? Oh yeah, and this is showing basically loss of the methyl, which I think is what happened in when it hydroxylated the methyl group back here, is that this happened, and then it kicked off to make the fourth metabolite, which is let's see if I can do it. Wait, sorry, there we are. To make this one. Yeah. Okay, now we have more. Let's see. I think there's more. No, there's not more. It's kind of hard to navigate. I think what I'm seeing here, but it's a little hard because of the web interface. What I'm seeing, there's something. There's this one, the rank fit. We're having a little trouble with this last one. Well, we got some of it. It looks like a double bond, maybe off the nitrogen, but I'm not too sure. Oh, okay. Oh, actually, I clicked this other button that's like additional less likely metabolites. So there's a whole bunch of metabolites potentially that it's predicting, and they're all kind of less likely. So it actually does a pretty exhaustive search. And yeah, and so that's pretty cool. Okay. And it's a little hard to see all of them individually, but some of these we can see, like hydroxylation of the CH2 up top, maybe hydroxylation of this position, hydroxylation of this position next to this nitrogen, and then of course if that happens, whoops, where is it? If that happens, if this happens and we get hydroxylation next to that site, then the oxygen could kick in and kick off methylamine, and that would make the aldehyde. So those are other possibilities. We're going to have a homework assignment on these things, and what we'll probably do is just have you pick the couple top ranked ones, top ranked molecules, metabolites. All right? Cool. So let's go back. A way to really look at each of these is to download the SDF file. We have not shown you tools on how to view SDF files. You have to download them, and we're not going to probably do that in this course. But there are definitely a lot of programs that you can look at these, and then you can look at each of the individual structures. Okay. All right, let's go back. So that's disipramine. How about, let's do atenolol now and look at some of the possible phase 1 metabolism. And it actually, yeah, the Glory server, I was saying, I thought it actually predicted phase 2, but it wasn't doing it very well. It doesn't do it. So it's not predicting phase 2, it's only predicting phase 1. And that's what the other tool we were talking about, the Biotransformer, is the Canadian website. That actually does a phase 2 metabolism analysis of this. But let's look at phase 1 metabolism of atenolol. And I got to get the smiles again. Here's the smiles. Okay. All right, so we're going to do the Glory prediction of atenolol. There it is. Oh yeah, what are the predictions while it's running? Predictions of phase 1 metabolism. I'll move the thing off. What might you predict could possibly happen to this in terms of phase 1 metabolism? I immediately am drawn to the nitrogen, the isopropyl amine, and this could very easily be hydroxylated, the CH. Not only is it next to nitrogen, but it's also a tertiary position, so there could be a tertiary radical, and then the radical gets oxidized to the alcohol. So this could happen, and then the alcohol could kick off acetone, make a ketone, acetone, and kick off the amine. I could also imagine maybe it might happen here, hydroxylation, and then maybe kick off the nitrogen, maybe make an alcohol that could be oxidized. Possible this alcohol could be oxidized because oxidative metabolism is pretty prevalent. Not too sure about anything over here. Definitely don't think the benzene would be touched. Might be wrong there. But with the para disubstituted benzenes, I don't think they're very reactive. Another possibility is maybe the next to this oxygen could get hydroxylated, and then the oxygen could kick this off and just cleave this bond, right? Cleave the ether bond to basically give you the benzene and hydroxybenzene, and like an alcohol. So definitely some things that I'm predicting. Most likely I'd be focused on the right side though, the amine. Okay, so let's take a look at the prediction of the metabolites of atenolol. All right, so let's look at the top. Here's the input molecule. Here's one. Okay, so it's actually seeing acetone. And where did acetone come from? I think it's acetone probably came from, let's go to this metabolite. Ah, yeah, just like I was showing, this position is very, very likely to be oxidized because it's via a tertiary radical. And so this tertiary alcohol could degrade to make acetone. So this would fall off as acetone, and then there's where acetone comes from, right? And then that would degrade to make two things, right? It would make acetone and the primary amine. And I see the primary amine over here. There it is, the primary amine, right? Okay, so we see those two are kind of like top metabolites. And also this ketone. Remember this, sorry, this one again. is not really very stable. These hemiaminols just degrade very readily, and yeah. Okay, and then the other one that we did not look at is this one, and this is just basically showing N-hydroxylation of the secondary amine. Yeah, that's very possible too. These things do further oxidation to nitrones and other high oxidation state nitrogen things. Okay, let's see. All right, so then they have the additional less likely metabolites. What do I predict? Maybe dealkyl or degradation of the benzene, maybe cleavage of the ether. Yeah, that's maybe what I think. I don't really know. Maybe oxidation of the alcohol. Let's take a look at what the server's saying. Well, okay, so the molecule's flipped over, but it's saying maybe N-hydroxylation of the amide. That's possible. Some kind of conversion of the N of the hydroxy group, which it was that was a metabolite before, right? Where the hydroxy group could get kicked off and make an imine. It looks like that's one, and then this is another kind of metabolite, maybe makes an enamine type derivative. These are all kind of low probability, but it's kind of fun to look at. Okay, there's the imine again. It looks like this is what I was leading towards. Oh no, actually this is saying maybe aromatic hydroxylation. Kind of a low likely thing, but it's possible. Aromatic hydroxylation. What else? Another aromatic hydroxylation. And we got some kind of weird stuff going on at the bottom, but yeah. These are just kind of degraded fragments. I'm not too sure where they're coming from, etc. Let's see. I'm looking for my ether cleavage. There we go. That's from the ether cleavage. So that's the hydroxybenzene, and that would come from this, right? So if this position got hydroxylated, as it's showing, the hydroxy group could kick off the para-hydroxy benzene derivative. So yeah, that's all possible. Low probability, and then just some more low probability ones. So the highest probability ones, though, were kind of related, like I said, to the I would say that hydroxylation of this position, and then the degradation to make acetone, and the primary amine. Okay, that was cool. Another. I would say that our prediction is pretty reasonable, and I was again drawn to the secondary amine over here. Okay, so this was the Biotransformer tool. I'll show. We did this once. I'll just show it one time for one of our simple molecules. This does phase 2 metabolite prediction. Let's try it once, just while we're talking about this again. And Nerd Glory doesn't do the phase 2 metabolite prediction, but it does phase 1. It seems to do that pretty well. Okay, so this was 4-hydroxytamoxifen. Remember, this is administered oral. One of the ways that this is administered orally, it's oxidized by P450 to hydroxylate the benzene. What we're going to do is the phase 2 prediction of this, and remembering that it's probably going to attach something here, whether it's glucuronidation or sulfate or acetate or something. So those are the predictions. Let's jump on and copy it. Okay, so I copy the smiles. Let's go over there. I think it was, let's Google it, Biotransformer metabolite. Okay, metabolism prediction. We're going to do phase 2 transformation. what I found is this tool was not very good at phase 1, but it seems to be pretty good at phase 2. And submit. Okay, so it predicted it. It showed 3 predicted metabolites. Let's look at them. And yeah, aromatic hydroxyglucuronidation, which, yep, there it is. The glucuronidate of the hydroxy group seems reasonable. N-glucuronidation of a tertiary aliphatic amine. I think this is unlikely because I just don't see tertiary amines being very reactive. Possible, but unlikely. Okay? And then sulfonation of the benzene with the hydroxy group. Okay. Cool. So yeah, there we are. That was a nice analysis of this. Last time we did this also for fusidic acid. It showed attachment of things to the hydroxy group. I'm not going to do that one again. Okay. And I think I'm going to probably stop this lecture today. I also, if I was predicting this using my knowledge of metabolism, I would say glycine glutamine conjugation maybe to the carboxylic acid, right? So to make a amide-linked conjugate out there. Yeah, I'm going to stop here. I want to put all these things together: the virtual screening and silico synthesis, homology modeling, docking, molecular dynamics. We'll cover these things in the next lecture, and I'll go through some of my research case studies, the GP41 inhibitors and SLC26A3 inhibitors, which is it's a chloride anion exchanger protein. Yeah, so let's stop today, and then we'll get into all these cool things, and then we'll be done with this section of the course. All right, have a great weekend.